Okay, this is Chemistry 2342, June 14th, Part B. So we're going to continue on with Friedel-Crafts, acylations and alkylations, and do a little bit more of comparing and contrasting, okay? So I said before that it's very hard to get long, straight chains in a Friedel-Crafts alkylation because of carbocation rearrangement. But I said there's a workaround, and the workaround has to do with creating the ketone first and then reducing it down, okay? So in the case of our long, if we wanted a straight chain, like a long straight chain on there, what we would want to do is create first the ketone and then take away that carbonyl portion of it and turn it into a CH2. And we have two opportunities to do that. And we have two reactions. One of them is in the book and one of them isn't in the book, but it's a very common one. So the first one I want to discuss is called the Clemmensen reduction right here. So in the case of any aryl ketone right here, where we have an alkyl group, we can use zinc metal and mercury metal plus an acid with a little bit of heat. And what it's going to do is it's actually going to end up protonating and then dehydrating this and adding two hydrogens to that carbonyl. So we're taking that ketone and we're basically reducing it down completely to give us a CH2 group here. So we're going from an sp2 hybridized carbonyl to an sp3 hybridized hydrocarbon, okay? Now, one thing to remember is if you have a nitro group on there, that will also be reduced by this mechanism, okay? Because any kind of zinc with HCl or tin with HCl will reduce down that nitro group to an amino group. So if that's what you want to do for both groups, that's great. If you want to do it specifically, you have to actually do a different reaction. To do that specifically, where you have a nitro group and you've reduced down your carbonyl, you need to do what's called the Wolff-Kishner reduction. And in the Wolff-Kishner reduction, what we do is we have two reagents for that. We have a thing called hydrazine, sometimes written N2H4. Sometimes it's written hydrazine, and sometimes it's written out like this. And then some kind of hydroxide. You just have to have hydroxide here. And so what it's going to do is that nitrogen is going to react with the carbonyl to make an imine, like we did in the last chapter. And then the base will reduce off that imine and give you your CH2 plus whatever alkyl group you had on there. Okay. Notice this will work with any of these products we get from the Friedel-Crafts acylation of benzene. Okay, so what does that mean? That means that we can use it as a strategy to create our straighter chain materials. So if we just wanted to, if we had a short alkyl chain like an ethyl group right here, we could do our Friedel-Crafts reaction just directly and generate that compound. However, if you have a substrate right here that can rearrange to form a secondary or tertiary carbocation, you will not form this as your major product. So the workaround would be to use the Friedel-Crafts acylation reaction to generate your ketone, then use either the Clemmensen reduction or the Wolff-Kishner reduction to get to your chain. Okay, so what would this look like? Okay. Well, this would look like something like here, okay? So if you wanted to get this propyl benzene right here with this straight chain here, you can't use just the propyl chloride right here, because once you generate your primary carbocation here, it's going to move over one carbon to give us a secondary carbocation, and our major product is going to be the isopropyl benzene right here. However, if you do want this straight chain or anything longer, you get the carboxylic acid derivative of the correct number of carbons you want. So notice here we have an ethyl group, but we have the carbon here. That's a total of 3 carbons in your carboxylic acid derivative. When you do that, that will create your ketone with the correct number of carbons. Then we reduce off our ketone here and we can get to the 3 carbon chain we were looking for. And we don't have any worry about a carbocation rearrangement because the acyl group is the attacking group, not the carbonyl. not the carbocation. Okay? Okay, so that's all the different reactions we have for doing this electrophilic aromatic substitution reaction, and some of the kind of drawbacks of them. You know, the Friedel-Crafts reactions, if you have strong electron drawing groups, it doesn't work. Okay, so we have to keep that in mind. So, but and we have the rearrangement problem in the Friedel-Crafts alkylation. So we need to keep this when we're talking about strategy on building the right molecule. We need to keep those two things in our head so that we build the exact molecule we're trying to build. Okay, now the next thing we need to talk about is substituent effects on the benzene. Let's say you already have a substituent on the benzene ring. Where's that electrophilic reaction going to take place? Well, it depends on what that substituent is. Okay, so let's start with thinking about, okay, instead of using benzene to start with, let's do something else like a toluene or an aniline, okay? So to decide how that's going to affect our reaction, we have to decide first whether it's an electron withdrawing substituent or an electron donating substituent. Okay, and so if we think about this, we're looking at an electrophilic attack, which means anything that donates electron density to the ring will make it more reactive. And anything that pulls electron density away from the ring makes it less reactive, okay? So we have to pay attention to that. Not only does it make it more or less reactive, it'll change where the reaction is going to take place, okay? So we have to look at all of the different groups we have on there and say, oh, are they donating or are they electron withdrawing, okay? Okay, so this already has come up a little bit in the fact that when we did a Friedel-Crafts alkylation right there, that the substituted product was more reactive than the unsubstituted benzene. And that has to do with the idea that the carbon-carbon bond is fairly nonpolar, but it acts as a weak electron donator. Therefore, the one that's substituted is now more reactive than the benzene by itself. And that's why we cannot get that just that one reaction if we did a 1-to-1 ratio. We have to use excess alkyl halide. Okay, so let's talk about electron donating effects and electron withdrawing groups. Okay, so in the case of this, so the generation of electrophile on the ring to form that carbocation. So once we form that carbocation, if you can stabilize that cation, it leads to an increase in that reaction rate. Okay, so if we have a cation there and we have some group that can donate electron density or maybe even contribute in the resonance structure, it will activate the substrate. So electron donating groups activate. Okay. Now, if we have an electron withdrawing group, that's pulling electron density away from the ring, meaning it's less likely to reach out and grab at the electrophile. Therefore, it's going to deactivate there and it will decrease the reaction rate. Okay. So the way we can look at that is how does it contribute to that partially positive charge shared on the ring in the transition state. And in the case of a donating group, that means this positive charge you just generated is not as positive. It's not a full positive charge because you've donated some electrons to help stabilize that charge. Okay. Now, if instead you have withdrawn some of these electrons and it makes that a harder charge or more positive charge, that's going to actually raise that energy required to get to that transition state. And that transition state is not going to be as stable because it's more positive, and therefore it's going to make it harder to get the transition state, and the intermediate is also not as stable. So it's going to slow the reaction down. Okay, so if we look at the energy diagrams associated with that, okay, if we have an electron withdrawing group, that's something that's going to pull electron density away from that ring. First thing that happens is our activation energy goes up because that energy of the transition state is higher than it would have been if we had no electron withdrawing group at all. Okay, so if we look at our energy here, right here, it takes extra energy just to get to that transition state, and that intermediate is at a higher energy than with just benzene. Okay. Now, if we have electron donating groups, so it's easier to form that partially positive charge because it's less of a positive charge, that means we needed less activation energy to get there. And if we draw this in a different color, so if we look at the benzene by itself, it actually took less energy if we have an electron donating group on there just to get to the transition state, and the energy of the intermediate is less as well. Okay, so it took less energy to get to the transition state, and the material is more stable. Therefore, it's easier to get to that intermediate, and therefore the reaction runs faster. Okay, so let's talk about the different groups we have available to us. And the first thing I want to talk about is the inductive electron withdrawing. What that means is that the substrate itself is more electronegative and is pulling electron density directly through that sigma bond that it is bonded to the benzene ring. Okay, so the way to look at this is anything that has a positive charge, a formal positive charge, or a partially positive charge can be an electron withdrawing group. Okay, so in the case of something like this quaternary ammonium salt, we have a formal positive charge on that nitrogen that's directly bound to the ring. It's inductively pulling electrons out of the benzene ring. Okay, now technically this alkyl group here are the alkyl groups on the nitrogen, not alkyl groups on the benzene. Okay. The other way to do that is if we had halogens on a carbon next to the ring. Okay, each of those halogens is more electronegative than carbon. Each of those halogens is pulling some electron density away from the carbon bonded to the benzene ring. Therefore, groups like CF3 or CCl3 tend to be electron withdrawing groups because those halogens are pulling electron density away from that carbon. Okay. If we think about it with a nitro species here, if we did the formal charges on a nitro species, we actually have a formal positive charge on that nitrogen, and it's directly bound to the benzene ring, so it is inductively pulling electron density away. Same for the sulfate. We have a formal positive charge on sulfur here, therefore it's inductively pulling that electron away. And anything with a carbonyl, because one of the resonance structures of carbonyl has a true charge separation, positive here and negative here. So there's always at least a partially positive charge on that carbonyl carbon, so it's always an electron withdrawing group. Even if we have other electron donating species, it just decreases the amount of carbonyl, decreases the amount of electrons it can pull away. However, it always is an electron withdrawing group. So that's the inductive electron withdrawing. Okay, now let's talk about how we can inductively, through that sigma bond, donate electron density back. Okay, so in the case of something like carbon, that carbon-carbon bond tends to be nonpolar. Okay, but the fact that we have an sp3 hybridized carbon and an sp2 hybridized carbon, it actually is a little bit polar. And therefore, alkyl groups, sp3 hybridized carbons, can donate electron density through hyperconjugation. Remember, hyperconjugation has to do with the orbitals, the sp3 hybridized orbitals overlapping with the p orbital. Okay, go back and look at in the book there if you don't remember the word hyperconjugation. Okay. So our alkyl groups have that little bit of donation, and so we tend to call them very weak electron donating groups. Okay. Now, in addition to that just direct electron transfer through that sigma bond, we also have resonance effects associated with it. Okay. So in the resonance effect, we can actually have lone pairs that are on the thing bonded to the benzene ring be able to contribute to resonance structures, okay? So in the case of resonance effects, you should always look for this lone pair either being contributing to stabilizing the charge or pulling away from stabilizing the charge. So the first one I want to talk about is resonance electron donation, okay? So resonance electron donation happens with any species you think of that has a lone pair on it that is next to the benzene ring, okay? So like amines, there's 2 lone pairs on this alcohol, there's 2 lone pairs on this ether oxygen, and even the lone pairs on halogens can contribute to resonance electron donation, okay? So what does that look like, okay? So if we had the electrons from the lone pair of this oxygen come in here and donate to give us a double bond here, we now have charge separation. We have a positive charge on this oxygen, a negative charge on the ring. And because of resonance delocalization, this negative charge can move all the way around the ring until we get back to our neutral species here. Notice only electrons are moving. We're talking about resonance again. Only electrons are moving. But the lone pair on this electronegative atom attached to the benzene ring can contribute to the resonance stability of the ring. Okay. So now let's talk about resonance electron withdrawing here, okay? And in most cases here, you still have lone pairs that you're looking for. However, the lone pairs are not directly bound to the atom next to the benzene ring. They are usually one atom adjacent. So in the case of something like benzaldehyde here, I said your carbonyl carbon is partially positive. So it has an inductive effect based on just that thing, that concept that this is partially positive. But we also have a resonance electron effect because one of the resonance structures of your carbonyl is having true charge separation, giving you a full positive charge on the carbon, a full negative charge on the oxygen here. And once you get that, you can then actually have a positive charge localized going around the ring through resonance, and then finally ending up back with aromaticity and ending up back with our neutral species. Okay. So resonance electron donation has an anion moving around the ring in resonance. Resonance electron withdrawing has a cation moving around the ring in resonance. Okay, so that is the key difference between the electron donating resonance and the electron withdrawing resonance, is that charge that you see moving around the ring through resonance. Okay, so let's do, since most of these compounds actually have one or both of these things happening, let's compare both the inductive and the resonance effect and how it does what, how it contributes to being an activator or a deactivator, okay? So I said before that the carbon-carbon bond, even in this, is not polar. However, we do have an sp3 hybridized carbon and an sp2 hybridized carbon. And we saw that it only has that inductive effect. There is not a lone pair and there is not charge separation. So there's no resonance effect associated with an alkyl group bonded to a benzene ring, okay? But remember, when we have things like carbonyls, we have both the inductive effect, direct bond, and a resonance effect associated with it, okay? So some groups have a reinforcing inductive and resonance effect. They are both acting as electron withdrawing, okay? So in the alkyl group, we don't have any resonance effect. We only have an inductive effect. In the carbonyl groups, we have both an inductive removal and a resonance removal, okay? So they're both enforcing an electron withdrawing group, okay? So let's talk about that a little bit. Okay. Sometimes you can have opposing inductive and resonance effects. Okay. For example, you can have an atom that is very electronegative, but it has lone pairs to donate back. So that means that by inductively, it's electron withdrawing, but because of that lone pair, it's electron donating by resonance. Okay. So let's look at electronegative atoms in particular. Let's look at neutral nitrogen or oxygen. Resonance dominates the effect, okay? That donating of the lone pair into the system dominates that effect. It is not just that nitrogen or oxygen is more electronegative than carbon. Those lone pairs are what's dominating the effect. Therefore, they are a net electron donator. Those lone pairs donate in, the resonant effects dominates. They are donators, okay? Now, halogens, on the other hand, even though they have 3 lone pairs on them, the inductive effects dominates, and therefore they actually pull electron density away from the benzene ring, okay? But those lone pairs will give us some selectivity on where the next reaction happens. Okay, and we'll see that in a couple slides. Okay, so electron withdrawing can happen by inductively or by resonance, and the different groups have different levels of importance. Okay, so let's consider both effects, okay? So something like an alkyl group, okay? So something like an alkyl group is an electron donating group, and it's an inductive electron donating group, okay? However, if we had something with like an amine or an alcohol on there, it is both an inductive withdrawer, but a resonance donator, okay? So that means that the resonance donation is more pronounced, and therefore they are both electron donating effects if you take both into account, okay? All right, halogens, on the other hand, they are more electronegative, and therefore the inductive effect is the primary effect, decreasing that. However, the resonance effect allows that inductive effect to be partially mitigated. So it's effectively an electron withdrawing group. However, it does contribute to the reactivity. Okay, so how do these different substituents affect the reaction, okay? So the first way that these substituents can affect the reaction is by changing the rate of the reaction. If you have an electron donating group on there, the reaction will always go faster than benzene itself. If you have an electron withdrawing group, it's going to go slower than with benzene itself, okay? So that's the first step in looking at the substituent that's already on the benzene ring when you're doing your next electrophilic substitution reaction. The next thing we have to take into account is, where does that new group go? Okay, you have already, on benzene ring, it didn't matter. All 6 sites are exactly the same. Now that you have something on there, now you have to say, oh, is it going to go next to it? Is it going to go ortho, which is the 1, 2? Is it going to go meta, the 1, 3, or para, the 1, 4? So now you have to figure out exactly where it's going to go. And that's the orientation effect of the substituent, okay? So all of the substituents can be divided into 3 general types, okay? Activating OrthoPara Directors. So when you're thinking activating OrthoPara Directors, think of something that has both resonance and inductive electron donating, okay? The second type is a deactivating OrthoPara Director. And in that, you have an inductive withdrawal, but a resonance donator, and we'll look at that. And then the last one is deactivating metadirectors. That's anything that has an inductive and or resonance with electron effect. Okay, so let's kind of summarize that into a little thing here. So if we were to take that and summarize that into a table, it would look something like this, okay? And the thing I want to draw your attention to is that OrthoPara Directors, except for the presence of the carbons ones here, notice there is a lone pair next to the bond bonded directly to the benzene ring, okay? So all of these strong activators have these lone pairs, okay? And remember, those lone pairs are able to contribute both inductively and resonance. And these lone pairs are predominantly resonance activators, okay? Now, if we have these these lone pair systems, however, we put a slight electron withdrawing group a bond away. So we have like an ester or an amide here, right here. We still have that lone pair available to us for resonance activation of our benzene ring. However, it's not as, does not have as much electron density as these strong activators. So they are moderately activating and they are OrthoPara Directors, okay? Now, our alkyl groups are weakly activating because they only have that hyperconjugative donation. They do not, they have a nonpolar bond, but they have a hyperconjugation donation, and that allows them to be weakly activating, but they are also going to direct ortho and para. And then these last ones right here, that's the special one. That's the one where we have the lone pairs available for conjugative electron donation, but we have very electronegative atoms. And so they want to, through the sigma bond, pull electron density away, but through those lone pairs, back donate them through resonance, okay? So when you start thinking about OrthoPara Directors, with the exception of the carbon here, think lone pair means OrthoPara Director, okay? So that being said, let's look at the other side with the meta directors. The ones, all meta directors are deactivators, okay? And what we're going to see in the common thing of all these is they all have a partially positive charge bonded directly to the benzene ring, or a full positive charge bonded to the ring, okay? So in the case of this group right here, this is the cyano group right here. If we looked at our resonance contributors here, we have a partially positive carbon and a partially negative nitrogen here. That's why it's deactivating, and that's why it's a meta director. If we draw resonance structures of the sulfonic acid group here, we'll see that there's a positive charge on nitrogen. All carbonyls and carbonyl compounds have a partially positive charge on that carbonyl compound. Therefore, they are also moderate deactivators, okay? Now, if we look at these strong deactivators, there's a full positive charge on nitrogen here. There's a full positive charge on this quaternary ammonium salt here. And these carbons have all their electron density being sucked away by an electronegative halogen. So that's why those are strong deactivators, okay? Notice all deactivators are meta directors, and all activators are orthopara. This is weakly deactivating. However, it's orthopara because of resonance effects. All right, questions on that, okay? So you can, I think you should be able to, using that electron, the lone pair kind of strategy, to look at almost any group plus the alkyl groups and the phenyl group here to say, oh, there's a lone pair on the atom bonded directly to the benzene ring. It should be orthopara directing, okay? In all the meta directors, you have a partially positive charge or a positive charge on the atom directly bonded to benzene ring. Think meta directors every time. So even if it's a functional group you don't know or you can't name, think about what that partially positive charge would be, or that partially, or where those lone pairs are, and you should be able to figure out whether it's an ortho or para director. Questions on that? Okay, we got about 15 more minutes, so I'm going to power through, and we're going to do a little bit more with ortho para direction. Okay. So I said that there's a couple different effects working with us when we have these OrthoPara Directors, okay? And one thing that helps us is that resonance donation, okay? Because of our resonance donation that we were talking about before, again, this lone pair can kick in, give us a double bond next to our benzene ring, and we're taking an anion and moving that anion around the ring, right? Remember, this is the electrophilic substitution, okay? Meaning we have something, those electrons are reaching out and grabbing some positive charge. So if by resonance, we have this negative charge moving around our ring, that makes it easier for reach out and grab that electrophile, that positive charge. And notice that we have that negative charge showing up at different places on the ring, okay? So if we remember our ortho and para and meta, our ortho is this one right here, this is our meta, and this is our para position here. 1, 2 is ortho, 1, 3 is meta, 1, 4 is para, okay? And we said that this resonance donation gives us ortho-para direction, okay? Let's look at our resonance contributors here, okay? In our resonance contributor, the first one here, we have our negative charge on our ortho position. In our resonance contributor, we have a negative charge on our para position. And in this resonance contributor, we have it on our other ortho position. And then it goes back to its neutral resonance contributor, okay? So what that means is that there is slightly more negative charge on the ortho and para positions through resonance than there are on the meta positions, okay? And because that partial negative charge makes it easier for it to reach out and grab that electrophile, that's why it is an ortho-para director. Does that make sense? This is really important because it tells us how it works and why it works.
Why isn't it a meta director?
Okay, so in our resonance contributors, is that negative charge ever on a meta position?
No, but I guess my question is why not?
Okay, because the electrons are being donated by the group that's already attached, right? And when we do resonance, we can only move electrons, right? So there is no way to move those electrons in from that oxygen and have them show up on the metacarbon. It would break conjugation to be able to do that. Does that make sense?
Mm-hmm.
So if we, because remember when we do resonance, we push 2 electrons and then we push 2 electrons and 2 electrons. You can try to draw that. You'll never get that negative charge to show up on those metacarbons if you've drawn the resonance contributors correctly, okay? You will always get them on that ortho and para carbon, okay? Make sense? Okay, go ahead and try that, and we're gonna actually do it for the meta director as well, so we'll show you that how it works in the meta director as well, okay? So let's move forward, unless somebody else has a question. Okay. All right, so I'm gonna move to the next slide here, okay? So in the case of our weak donators, we have the same thing kind of happening here in the fact that when we have the electron come out and grab at the electrophile, we're generating a partially positive charge on sites that can be stabilized by that weak inductive effect, okay? So for example, if we have this methyl group here, remember that's a weak activator because all it has is that little bit of hyperconjugation donating electron density back into the system, okay? So it's not activating the system very much because it's not giving us that partial negative charge on the ortho and para. However, when we do have attack by the electrons to the electrophile, we generate a partially positive charge on the carbon next to it. And by resonance, that moves over to the other carbon. And by resonance, that'll move over to the carbon with that weakly donating group, okay? So that means this carbon with the positive charge on it is stabilized to some extent, okay, by that weak inductive effect, okay? So let's do that again for the para. Let's do it at the bottom first right here. And if we have attack by these electrons coming out here at that parasite, that's going to generate our positive charge next to it, like in the same mechanism here. When we move that up, we again get that partially positive charge, stabilized by hyperconjugation. And then when it moves back over here, it is less stable. That means that this resonance contributor is a little bit more stable than either of these, and therefore that makes the para attack a more positive, it has a more stable resonance contributor. Okay, now let's go to the other extreme. So we've done ortho 1, 2, we've done para 1, 4, let's do 1, 3 and see how that positive charge moves around and whether or not it is stabilized by that weak donator, okay? So in the case of the meta attack, we would generate the positive charge. Let's do it in red here. The positive charge here, because it has to be adjacent to that. And that positive charge could generate down here next to it, right here. And then by resonance, we can generate it here. Notice at no time does that positive charge wind up on the carbon that has that inductive stabilization effect, okay? So at no time can we stabilize these cations with that inductive effect, making all three of these resonance contributors, the net result of all those resonance contributors, are less stable than the net contributors of the ortho and para, okay? So the net result is if you can put your electron donating group in the presence or right next to where your positive charge can be stabilized, it activates the system and directs it ortho-para. Okay? So let's do it again, but let's do it with the halogens, okay? The halogens, I said, were weakly or deactivators. However, they were OrthoPara directors. Let's see why that works. Okay, and what we're going to see is some of the same resonance structures we just saw here. Okay, so in the case of like chlorobenzene right here, we would have a possibility of getting ortho, meta, or para attack. But let's look how that chlorine, which is inductively withdrawing, can possibly resonance stabilize that positive charge. Okay, so if we look at the first attack in an ortho right here, that's the one next to it here, we're going to get our positive charge form on that adjacent carbon, and then by resonance we'll move it over one position, over two positions, and by resonance we can move it over here. Okay, so we have a partially positive charge next to an electronegative atom. Okay, you're thinking, oh, wait a minute, inductively it does not want to be there. However, it has lone pairs that it can donate in here and stabilize the positive charge off the ring. We have a new resonance contributor here where the positive charge is completely removed from the ring. Okay, so, and then of course, if those electrons come back in, we'll go back around. Okay, so we have a fourth resonance contributor that gives us that attack. Okay, and so this fourth resonance contributor adds to the stability of the overall system. All right, let's look at it with para attack. Okay, with para attack, we're going to get the same thing where we generate our positive charge on this carbon. It can then move up to the one next to the chlorine, which can then pull in this lone pair to generate a positive charge outside the ring, and then it can come back in and generate our other resonance contributor. Okay, so notice we have that nice stabilized fourth resonance contributor where the positive charge is on our electronegative atom. Okay, all right, now let's do the meta attack and see if we see that same contribution to that stability. Okay, so if we have attack by our electrons of our benzene ring, it's going to generate a positive charge at the ortho position right here. And by resonance, it's going to skip over the atom that the chlorine's on, giving us our positive charge here. And then, of course, it'll move back to being adjacent to where the electrophile was attached. Okay. There is no way for those the lone pairs on the chlorine to contribute to giving us another stable contributor. We only have 3 resonance contributors in the meta attack. In ortho and para, we have 4 resonance contributors. Okay, so that's why even in the case of a halogen that is inductively electron withdrawing, it directs ortho-para. By induction, it deactivates. By resonance, it directs ortho-para. Okay, so things with lone pairs that can contribute to a resonance structure are going to be OrthoPara directors. Okay, the only reason the halogens are considered deactivators is because of the inductive electron withdrawing effect. Okay, so questions on that? Are we starting to see why by adding an extra resonance contributor, it becomes more stable? More stable means it's going to be more likely to form as our intermediate. If it's more likely to form as our intermediate, it's more likely to give us our product. Okay. So now let's look at the strong activating. Okay. In the strong activating, we're going to see the exact same thing. We have an inductive effect already adding electron density to the ring, stabilizing that positive charge. But we also have the resonance addition to the system as well. So we have activating just by having extra electron density there to reach out and grab that electrophile, and we have resonance. So in the case of here, we're going to see with ortho and para, again, we get those same resonance structures where it's going around the ring, and that's just the inductive part right there. And then we get our next resonance contributor, our 4th resonance contributor, giving us that charge off the ring, leading to the ortho attack being stabilized by that 4th resonance contributor. If we meta attack right here, we actually end up skipping over that electron-rich range, that electron-rich atom. We have the positive charge move from this side to that side, going in that direction there. So it cannot, by conjugation, stabilize that positive charge, and we only have 3 resonance contributors. Okay, and of course with para, we again can have that positive charge move to where we have the electrons from the electron pair from the donator come in and give us a 4th resonance contributor. So all strong activators are strongly activating because of the resonance component, as well as that inductive electron donating component. Okay, we're coming up on 140. Let's see. I'm going to do meta directors next time. So what I want you to focus on is these OrthoPara direction has everything to do with that 4th resonance contributor. Okay. The OrthoPara activation is either a combination of inductive effect and resonance effect. The OrthoPara deactivation has everything to do with an inductive withdrawal, but a conjugative or a resonance donation. All right, questions on OrthoPara? And while I'm waiting for that, I want to go back to here and have you look at all these things again, okay? All right, and the thing that you should see in all of these is on the OrthoPara directors, we have those lone pairs of electrons that contribute to the resonance, or a weak hyperconjugative effect. Okay, lone pairs, lone pairs, lone pairs, weak hyperconjugative effect. OrthoPara Director. All right, questions? Okay, so what I'm gonna do now is I'm gonna stop recording and I'll answer questions for a little while. I do have a phone call at 1:45, so I have a few minutes for questions. All right, let me stop recording.